Hello, everyone. This is Holly Thorne with the City of Oklahoma City Stormwater Quality and the Central Oklahoma Stormwater Alliance, or COSWA. I'd like to officially welcome everyone to this special training event. If anyone is interested in receiving a certificate of attendance for this training, please send me an email to request it. I will need your email address to be able to send the certificate to you, so please don't request these in chat. If you have any questions about the certificates or haven't received one within a couple days after this webinar, please feel free to email me. I have placed my email address into chat already, so feel free to use that when necessary. Please be sure to keep ourselves muted during the presentation. If you have any questions, simply type them into chat. We will have time at the end for questions. Today, we will be hearing from Brian Roche, a graduate research assistant with Auburn University. He will be sharing information on his presentation titled Improving Rock Check Dams Through Full-Scale Testing. Brian is a PhD candidate in the Auburn University Department of Civil and Environmental Engineering, completing research at the Auburn University Stormwater Research Facility. Originally from Orlando, Florida, Brian graduated from the University of Florida with a bachelor's in civil engineering and from Auburn University with a master's in civil engineering. Brian has completed research on improving construction stormwater management practices to protect our nation's waterways from sediment pollution from construction projects. His master's thesis focused on enhancing sediment capture and water quality treatment performance of sediment barriers, such as silt fence, wattles, and slash mulch berms, and determining the performance of vegetated buffers and sediment capture. Recently, Brian has completed research on the erosion prevention and sediment capture capabilities of rock check dams through cost-effective modifications and is working on improving risk and resilience-based design guidance for other erosion and sediment control practices. He's expected to graduate with his PhD this fall.
Thank you, Holly.
Yeah, no problem. I will stop sharing my screen and let you begin your presentation.
All right. Is everyone able to see that all right?
Yes.
Perfect. All right. Good morning, everyone. Thank you for taking the time out of your day to listen to me talk about some exciting research we completed recently for the Iowa DOT on improving their and other rock check dam standards through full-scale testing. So I'd first like to recognize and thank the rest of the research team that made this happen, especially our three co-principal investigators, as well as the undergraduate and graduate students that assisted on the project. So quickly, just wanted to touch base on the plan for the presentation. We'll just start with some background, then go through some research objectives, our research plan, our literature review, and then our testing methodology results and kind of recommendations from all this. So runoff on construction projects, especially highway construction, is often directed into conveyance channels. These channels can be at risk of erosion, especially before stabilization due to high flow velocities, which can also prevent that stabilization from occurring. So shear stress is the leading driver of erosion in channels and is based on the flow depth, the unit weight of the fluid, and the slope of the hydraulic grade line. And earthen channels don't have much allowable shear stress before erosion occurs if they're not stabilized. Even this 4-inch depth flow would be erosive for this earthen channel. So vegetation being established in channels can increase the shear stress capacity of a channel and prevent erosion from occurring. However, a lot of times on construction projects, vegetation has not yet been established. Other erosion control practices, such as erosion control blankets and turf reinforcement mats, may be used to increase the shear stress capacity of channels and prevent erosion. However, channels with more flow can increase the shear stress to erosive levels for both vegetated or lined channels. So to improve these protections of these channels, ditch checks, such as the rock check dams we're going to talk about today, are installed to reduce the slope of the hydraulic grade line to effectively zero, and therefore reducing the shear stress to zero and protecting the channel from erosion. However, as you can see here, these are only effective if they impound the full height of the installation and are able to form that pool of slow-moving water that reaches the previous installation. Improperly installed, designed, or maintained ditch checks or check dams that do not impound flow to the top of the installation are going to have areas of channel that are still subject to those steeper hydraulic grade lines and erosive conditions. So you'll have some areas protected from flow. However, upstream of that hydraulic jump or the location where that flow transforms from high energy erosive conditions to that slower moving non-erosive flow, will be located in the channel with kind of highly erosive conditions upstream that still have that high slope of the hydraulic grade line. So like I mentioned, ditch checks are used to prevent these erosive flows by just forming a pool of water upstream, slowing velocity. These primarily function as an erosion control practice, but they do have some secondary benefits in sediment capture through deposition in that impoundment formed upstream. Common ditch check practices are wattles, silt fence, and then rock check dams. With rock check dams kind of offering advantages over the others, they're commonly recommended or used in channels where either high flows are expected or where other installations have failed due to higher flow rates. Because these rock check dams, because being formed of rock, they are less likely to be able to wash out due to high flows. So these ditch checks are typically installed in series in a channel with multiple going down the channel, and they're spaced apart based on the theoretical ponding length, with the top of the downstream practice being at the same elevation of the bottom of the practice immediately upstream, so that if it impounds all the way to the top and overtops, you're going to have that pool of water stretching all the way from one installation to another, make sure that the entire channel is protected. However, in practice, a lot of times this doesn't happen if, such as with a high flow through rate for a ditch check, you're going to have portions of channels that'll be unprotected from those erosive flows. So kind of reads us into the objectives for this research, which is to evaluate the existing Iowa DOT rock check dam standard through large-scale testing, and then use the testing results to develop and evaluate efficient, cost-effective rock check dam installation enhancements. So to complete these objectives, we developed a 5-stage research plan, starting with a literature review with the goal of aiding in identifying modifications and developing testing methodology, leading kind of into our development of our testing methodology, and then conducting our full-scale experiments and analyzing data. And these tasks 3 and 4 was kind of an iterative process where we analyze the data from some tests and use that data to develop modifications to then evaluate further. And then our final task was taking all of his data and recommendations and developing a final report that outlines the literature review, the methodology, the results, and the recommendations. So our first completed task was the literature review, which focused on investigating the rock check dam standards for other states and jurisdictions, the Iowa DOT's usage of rock check dams, and then past research on ditch checks as a whole and rock check dams. So first, we looked at rock check dam installations for DOTs across the U.S., as well as some international standards. We saw a good bit of variation in components, such as the size of rock, the height of the check dam, the use of overlays, underlays, the depth of the weir to allow for controlled overflow, and if they're trenched in. We did see, however, that most are similar to the Iowa DOT standard, about 2.5 feet tall, with a 6-inch weir, composed of large rock only, with a geotextile underlay and excavation beneath the installation. We did, however, see that some jurisdictions used components to increase impoundment, such as 2 using geotextile overlays and then 11 using a small choker stone on that upstream face. So the Iowa DOT standard, like I mentioned, it used large rock alone with a top size of 250 pounds, at least 50% of that rock being over 90 pounds, and at least 90% being over 5 pounds. They had no overlay or choker stone, so no additional components kind of aid in the formation of impoundment besides the rock. There's also a geotextile underlay going under the entire installation to prevent undermining, as well as a 6-inch excavation in the channel that the check dam was installed in. So we also wanted to look at how much Iowa actually used these practices. So we looked at 5 years of bid tabs on Iowa DOT highway construction. We found that in total they spent over $4 million on these rock check dam installations, in both installing, maintaining, and removing these practices, with an average cost of over $500 per check dam. So this really indicated there's a research need to make sure that these funds are being used effectively. So kind of diving into some past performance testing. So most have been completed on other practices, typically wattles. And this research is divided into 3 main categories: field monitoring, small scale testing, and large scale testing. We didn't really see much testing on rock check dams. We did find some large scale research that we'll get into. So small scale testing is primarily in flumes, and this has really kind of been focused on wattles. And a big takeaway from these fume evaluations are that they indicated that most practices do not impound to that theoretical level, as you can see in this graphic here, that spacing guidance is based on, even if they're able to impound to the top of the practice. Additionally, a performance measure called impoundment length and depth efficiency was developed that indicates the percent of the channel that's protected from erosive flows. And the actual impoundment length in these tests was determined based on the length of that subcritical flow, that length from the upstream face of the practice to the hydraulic jump, and compared to that theoretical standing pool to develop an efficiency. One field study that we focused on was completed in Iowa a few years ago. It evaluated standard and modified ditch check installations, including silt fence and wattles and rock check dams. Wattles and silt fence were able to be improved to prevent occurrences of failure. And the Iowa DOT standard rock check dam was found to be kind of ineffective at preventing erosion due to undermining and high flow through rates. But unfortunately, these installations were not able to be modified due to changing site conditions, which is a common limitation of field monitoring studies, along with different storm and site conditions that can make comparisons difficult between different sites. So large-scale testing, such as those completed by Donald et al. At our research facility back in 2014, kind of attempts to reduce the limitations of small-scale testing and field monitoring by evaluating full installations under controlled conditions. So this particular study found that the large rocks of the Alabama DOT rock check dam standard failed to protect more than half the channel, with having an impoundment efficiency of only about 48%, and that this performance was increased using either a coarse aggregate choker on that upstream face or a geotextile overlay. So our literature review as a whole, we found that there was a clear disconnect between rock check dams commonly used and then prior performance testing results. Kind of seeing that they're spending a lot of money, all DOTs around the country are spending a lot of money in these installations that can definitely be improved. So from there, it leads into our second task, which was the development of our testing methodology. So all of our testing occurred at the Auburn University Stormwater Research Facility in about 10-acre outdoor lab space that's dedicated to producing innovative and practical solutions for stormwater management through interdisciplinary research, product evaluation, and hands-on training, with testing occurring in this channel right here. So this testing said was completed in a channel with a downstream sediment basin that's representative of those found on Iowa highway construction projects. The entire channel was lined with geotextile to prevent extensive maintenance between tests and to allow for repeatable results to make sure there's not any of those variables affecting results. But in practice, these channels would likely be earthen and unlined. So we introduced flow from a nearby supply pond into a weir tank with a series of valves that allow for the adjustment and monitoring of introduction flow rates. And after the flow leaves that weir in the tank, it flows into a flow transition area that aims to reduce that initial energy to conditions representative of Iowa highway construction projects. So the geometry of the standard Iowa DOT roadside channel has a 10-foot bottom width, a 5-foot depth, 3-to-1 side slopes on one side and 3.5 on the other. So in our test channel, which you can see here, we installed string lines to serve as measurement cross sections, approximately 5 feet apart. We installed 16 upstream and 2 downstream to make sure for the upstream, we wanted to make sure we're going past that maximum theoretical impoundment length, which we found to be 63 feet, so kind of between cross section 3 and 4 here. We found that based on a survey, finding the height of the elevation of the channel that would be equal to the height of the check dam downstream. And we also installed those 2 downstream cross sections to make sure we're evaluating conditions immediately after the installation. So at first, we're primarily looking at hydraulic performance of these installations due to their use as erosion control practices and slowing flow. So each cross section, we measured flow depth and velocity at 3 locations to generate a full flow profile. We also measured the distance from the front face of the installation to that hydraulic jump to compare to that theoretical impoundment length of 63 feet to develop an impoundment efficiency. We also wanted to evaluate dewatering time to make sure that practices can recover from storm events and be able to withstand another one coming in after, as well as if there's extended dewatering times, you'll have difficulty establishing vegetation. So first, we evaluate our standard installation, followed by 7 modifications. Each installation was evaluated 3 times for hydraulic performance under both a low and high flow rate. So that low flow rate is representative of the peak flow of 1/2 acre in Iowa, and that high flow rate is 1 acre to kind of indicate performance under various conditions. Developing these modifications was an iterative process with the overall goals of increasing performance and reducing costs. So after we evaluated the standard and 7 modifications for hydraulic performance, we selected the highest performing one with also consideration for cost and installation efforts to be our most feasible and effective installation, or our MFEI. So after completing the hydraulic testing, we evaluated both the standard and the MFEI under sediment-laden conditions to determine improvements in secondary sediment control benefits. So the sediment-laden testing used an sediment introduction rate of about 65.4 pounds per minute, centuries by hand, and a flow rate of 1.7 cubic feet per second. This rate's identical to testing of past Iowa DOT sediment basin practices using that same testing apparatus that we're using to allow for comparisons. Additionally, during testing, we took water quality samples every 3 minutes during flow introduction period, and also regularly through that dewatering period afterwards. And we took these samples at 3 locations, one upstream of the theoretical impoundment length to serve as a kind of introduction of turbidity and total suspended solids, as well as immediately upstream of the check dam and downstream to determine overall treatment. So our third test is actually getting into the completion of our large-scale testing. And first, we're going to start with the hydraulic testing results. And this was just flow straight from the supply pond with no additional sediment added. So our first test was on the Iowa DOT rock check dam standard, which you can see here. We had large rock, a geotextile underlay, and an excavation beneath. And here's what it looks like in action. You can kind of see very little impoundment formed upstream. One thing we also wanted to consider through all this was keeping cost in consideration to make sure our results are practical and implementable. So for each installation, we did an approximate material cost estimate, with the standard being about $673 of material. So the standard installation, it only impounded an average of 6 feet upstream under those high flow conditions, which really indicates that over 90% of the channel was still subject to those highly erosive flows. And we really saw, looking at flow velocity, it only reduced flow velocity at that first cross section immediately upstream, and also immediately jumped back to highly erosive flows downstream. So our first modification intended to see if the excavation beneath the installation actually aided in the formation of impoundment. Excuse me. The removal of this excavation would save both material costs, with a reduction of approximately $150 of material, while also reducing installation efforts and costs. So as you can see here, it performed very similar to the standard installation with very little impoundment formed upstream. And you can actually see that hydraulic jump on the left of the screen is only a few feet from that front face of the check dam. So we ran some statistics. We found that there was not a statistically significant difference in impoundment formed compared to the standard, kind of indicating that that cost can be reduced by just installing that installation on grade. So due to this conclusion, most of our other modifications were installed on grade due to us not seeing any degradation of performance with the removal of that excavation. So through these two installations that used the larger rock, we really saw that flow was able to pass through large pores between these rocks, kind of leading to a lack of impoundment formed. So that led us to our second modification, where we're trying to improve performance using a smaller rock gradation that results in smaller pore openings. So for this, we used a gradation of rock that's often used on Iowa DOT construction projects, which they call their erosion stone. It's a nominal 6-inch diameter and between 3 and 9 inches. We wanted to make sure to use a gradation of rock that's actually available in Iowa to make sure it's implementable. So this installation did actually use that excavation from the standard, as we were only trying to determine if that rock gradation improved performance. And additionally, this reduced approximate material cost due to this material being less expensive than the larger rock. So as you can see here, so that small rock in action, we did see that the smaller pore size improved impoundment formation, with a larger pool of impoundment being evident upstream of the dam. Here's kind of that better angle if you can see that length of impoundment. We found that under that high flow rate, we're able to get to approximately half of the channel. However, this means that still about half that channel is being unprotected from those erosive flows. Additionally, one thing we were a little bit worried about switching to smaller rock was washout. We did not observe this even under higher flow conditions above that 1.7 cubic feet per second. So based on the previous research, we added a geotextile overlay to that standard rock gradation. This was secured 3 feet upstream with sod staples every 6 inches, and then on the downstream of the installation just with loose rock. We saw a slight increase in material cost compared to that large rock with no excavation, due to that cost of geotextile, but this was still beneath that standard cost due to not having the excavation that requires more material. So this did considerably increase impoundment formation. to about 78 and 77% for those low and high flow rates. However, we did see a couple of deficiencies. One of these being extensive dewatering time. Like I've mentioned before, if this pool of water is able to remain in the channel for extended periods of time, you're going to be less likely to have vegetation established in the channel, which is the final goal of these projects. So additionally, as you can see here, we saw flow was overtopping at the low points between these large rocks and not impounding at full design height of the installation, leading to kind of less impoundment form, as you can see, with only 78% of the channel being protected. So the first of these deficiencies we wanted to tackle was that extended dewatering time. So to improve upon this, we added 9 1-inch holes, cut in just a cross configuration with a standard box cutter. These were in 3 columns, spaced every 1 foot vertically, with one of these columns being at the center of the channel, and then the other 2 columns being at the edge of the bottom width. And here's what those holes looked like a little closer up. It's effectively a 1-inch hole, cut in that geotextile to make sure that we're able to dewater more effectively. And this also had an identical material cost to that other installation with the geotextile overlay. Let's suppose a slightly higher installation cost if you need to get in the channel and cut those holes. So we found very similar performance with these dewatering holes to the geotextile overlay, with no statistically significant difference in hydraulic performance. While this reduced dewatering time to about 7.5 hours on average from that maximum of 96 that we saw without the dewatering holes. Our next modification, we wanted to see if we could improve that design height and have a more consistent height of that weir in the center. So to do this, we employed that smaller rock gradation with the geotextile overlay. So with that first installation with just that smaller rock, we kind of found that it was easier to form the check dam and reach the proper size specifications more consistently. Additionally, due to this being the cheaper material, it slightly reduced material cost to approximately $433. So we found that this did increase impoundment due to that having that more consistent height of the weir. As you can see in this image, flow is kind of going over that entire width rather than finding those low points between the rocks. And we did, however, see that extended dewatering time that was associated with just the geotextile overlay becoming clogged with sediment over time. I mentioned this allowed for that more consistent height. We still saw those extended dewatering times. So our next modification we evaluated was using that smaller rock gradation, the geotextile overlay, but adding the dewatering holes. This had the same material cost as that previous installation. So we found very similar results for that smaller rock with the geotextile overlay, however, with a reduced dewatering time. And for these tests and the previous modification, we actually installed a pressure gauge immediately upstream of the installation that's able to measure water depth to better evaluate how these installations dewatered. So you can see a comparison between the installation with the geotextile overlay in blue and the dewatering holes in orange. So this increased with each subsequent test, even with those dewatering holes, showing that maintenance of these dewatering holes is required to ensure consistent dewatering times. So our final modification aimed to kind of further reduce the material cost of installations by reducing the bottom width perpendicular to flow from 6 feet to 4 feet by making those side slopes of the installation steeper. And this reduced material cost further by an additional $129 approximately to about $300. And testing results of this installation showed similar performance to other installations with those geotextile overlays, dewatering holes, and that smaller rock gradation. Here's just kind of an overview of our hydraulic testing results with our cost estimate. As you can see here, our modification 7, which has that reduced profile, no excavation beneath, a smaller rock gradation, and a geotextile overlay with dewatering holes. It performed the best out of all our installations and was also the least material cost. Due to this, it was selected as our most feasible and effective installation. We also saw similar results with that high flow rate. And one kind of big thing we saw here was that the geotextile overlay, all those installations with that overlay kind of performed similarly, having the highest impoundment length, so the most area protected of the channel, as well as the most cross sections with that less erosive subcritical flow. So you can see here, the large rock alone with the standard and the installation installed on grade showed a lack of impoundment formation, kind of due to those large pores in the rock. The small rocks significantly increase impoundment compared to those first two, but only still to about half that theoretical maximum where that next upstream installation would be located. Additionally, we saw that all the installations with the geotextile overlay performed very similarly in impoundment formation. However, none of these were able to reach that theoretical maximum of 63 feet, which shows that you might spacing guidance may need to be adjusted, or you might need to extend a geotextile underlay further down to protect erosion in that area of the channel. So we also wanted to make sure to run some statistics to prove our findings. So we ran a multiple linear regression model at a 90% confidence interval to determine how each installation component impacted impoundment formation. So we used a base condition of no rock check dam installed with no impoundment formed. And then a value of 0 was used for the components used in the standard and 1 for the modifications. So for example, for our data analysis, standard installation would just have a 0 in all of these components, the gradation, excavation, geotextile overlay, while the small rock gradation would have a 1 in that category. So we saw high p-values for the excavation, the dewatering holes, and the reduced profile. And this indicates that these did not statistically impact impoundment formation, while also providing other benefits. So due to the lower p-values of the rock radiation geotextile overlay, we found that those were the only components that impacted that hydraulic impoundment formation. So we also wanted to investigate flow velocity. A few takeaways from here is that we saw an immediate increase in velocity downstream of every single practice to these erosive conditions. We also saw that, like the other results, that those installations with the similar components, such as that overlay, performed similarly, reducing flow to non-erosive channels for much of the channel upstream. So we saw similar results for the high flow as well. One interesting result here that we found is that even in the impoundment formed by installations with that geotextile overlay, we saw average flow velocities at or above those permissible values for highly erosive soils, indicating that additional erosion control practices may be required in areas with channels that have highly erosive soils. So we're able to come up with a few conclusions based on the data analysis of the clean water hydraulic tests. So we found that excavation beneath the installation provided little benefit while increasing cost. That smaller Iowa DOT erosion stone outperforms that standard Class D revetment that's used for the standard check dams due to both the smaller pores without the geotextile overlay, as well as the more consistent weir heights with that geotextile overlay. We also found matching past research that addition of a geotextile overlay is vital to ensure installations impound flow and protect those channels from erosion. And that dewatering holes in the geotextile overlay kind of reduce those extended dewatering times without adversely impacting performance. We also found that reducing the width of the installation can reduce material cost without impacting performance or washout occurring. And that additional erosion control practice may be necessary if the soil of the channel is particularly erosive, especially downstream. And we even saw that even the highest performing rock check dams did not protect the entire channel from erosive flows, kind of indicating that spacing guidance may need to be adjusted or recommending an extended underlay a few feet downstream of the installation. So after the completion of these hydraulic clean water tests, we moved on to the sediment-laden testing of the standard and the selected most feasible and effective installation. So just like we did in those hydraulic tests, we saw high flow-through rates and low impoundment lengths for the standard installation due to those large pores between the rock. So this lack of impoundment formed upstream led to a lack of sedimentation able to occur. So we saw under 10% of that introduced sediment was captured upstream of the installation. To measure this, we compared our known amount of introduced sediment. We removed all the sediment that was captured upstream after 3 tests, dried it, weighed it, and compared the two. So in our water quality results, we primarily focused on turbidity. We did not see any water quality improvements. We found that there was no statistical difference in turbidity found between samples taken upstream of the installation and downstream, showing that no water quality treatment was occurring. So said that most feasible and effective installation of that geotextile overlay of smaller rock with dewatering holes and the reduced profile was also evaluated under these sediment-laden conditions. which you can see here with that additional impoundment length formed. So we saw an increase in sediment capture to about 72%. And one interesting thing we saw was that there was a lot of that coarse material was deposited immediately upstream, or immediately downstream of that hydraulic jump as soon as that flow was able to slow down. So here are water quality results. A couple interesting things we see here. So in other practices, such as silt fence sediment basins, the water at the surface of the impoundment formed immediately upstream tends to have lower turbidity than that bottom impoundment, which we did not see here. This lack of a difference between these two was likely due to short circuiting that we saw due to overtopping. So additionally, unlike the standard installation, we saw a clear pattern over time looking at that water quality. So we saw what's called a first flush effect, where the first flow introduced after each test redisturbs the sediment that was there, increasing the turbidity immediately before it kind of stables out, evens out at about 600 NTUs as that dewatering occurs. So on the standard and most feasible and effective turbidity samples, we ran 2 sets of statistical analysis to determine any improvements in water quality treatment. At first, we compared all of the samples taken at the discharge for both the standard and the most feasible and effective installation, finding that the turbidity of the discharge for the MFEI was significantly less than that of the standard installation, showing better water quality. Then we wanted to see if this was just due to that slightly extended dewatering period, or if water quality samples taken during the test were also lowered. So we ran a paired analysis where we're only comparing samples taken at the exact same time in the test, and we did find that the most feasible and effective installation had lower turbidity for the paired samples as well. So these two analyses together indicate that the MFEI did have improved discharge water quality compared to the standard. So overall, we saw that the improvements for the MFEI increased performance in sediment capture and water quality treatment. However, we saw that the treatment and sediment capture of even these improved installations were well below those found in the evaluation of other sediment control practices using those identical conditions. But we did find that the sediment capture was very similar to that found in a forebay composed of a rock check dam with a geotextile overlay under the same conditions. So kind of overall, due to a relative lack of sediment capture and high discharge turbidity, even of this most feasible and effective installation, compared to other sediment control practices, show that these are primarily still an erosion control practice. However, these improvements can prevent erosion and capture some sediment, which can lower the loading on downstream sediment basin practices or lower the risk of sediment-laden discharge from a site. So some of our overall conclusions, we found that installation with no excavation, that smaller Iowa DOT erosion stone, a geotextile overlay and dewatering holes, as well as reduced width, had the highest performance and the least material cost. So we selected that as our most feasible and effective installation. And this installation compared to the standard installation increased impoundment length from 6 feet to 58 feet, increased sediment capture by 63% of that introduced, and reduced discharge turbidity. So we also wanted to look back at that material estimate and those bid tabs we looked at in the literature review. So had the Iowa DOT used these modified installation, we would have expected them to save approximately $800,000 on material alone during that 5-year period. And that doesn't even consider additional savings in installation costs by removing that excavation, decreased maintenance of downstream practices due to slower sediment loading, or downstream remediation of sediment-laden discharge. So overall, here are recommendations for implementation in Iowa and in any other area that's looking to improve their rock check dam standards. Is adding that geotextile overlay to facilitate additional impoundment, using a smaller rock to both increase performance without the geotextile, reduce costs, and ensure proper heights of installations. Adding dewatering holes in the geotextile overlay to ensure impoundment does not remain there for excessive periods of time to make sure that vegetation can be established in the channel, as well as removing any excavations and reducing width to further decrease material costs. And then kind of due to those high downstream flow velocities and each installation not reaching that maximum theoretical, extending that geotextile downstream to prevent erosion there. Additionally, we recommend to use additional erosion control practices in channels with highly erosive soils, just to make sure that you're preventing erosion from occurring. And with that, I'd be happy to answer any questions. Additionally, the final report for this project is published and available if you're interested in reading more about the project. Thank you.
Perfect. Thank you, Brian. Great presentation, great interesting results at the end. We had one question from Derek Johnson from OKC, but it has disappeared in the chat. Derek, if you'd still like to ask that question, you can unmute yourself and ask Brian directly.
No, I'm good. I actually answered my own question here.
Okay, perfect. Just wanted to make sure. Brian has offered his slides in a PDF format. If anyone is wanting today's presentation slides, feel free to email me at the same email to request that certificate. I placed that back into chat just in case, just putting it at the forefront so everyone can see it. Okay, so Derek Johnson does want to know, is the Iowa DOT considering a standard revision based on these conclusions?
So yes, I believe so. So we presented these results to them a few months ago. They seemed very interested. It sounded like they were going to install them on a couple highway construction sites just to make sure that contractors are comfortable with installation. But yes, I believe so.
Great. And then Wayne Craney with DEQ asked, geotextile mill thick or woven or not?
So I don't know the exact thickness, but it was an 8-ounce filter fabric and it was non-woven. So it fit their standards for use as the geotextile underlay. Because we wanted to make sure that all the materials used were available and commonly used on these Iowa DOT highway construction projects, just to make sure to not provide any difficulty in actually implementing them.
Great. Okay, like I said, my email is in chat for everyone who needs a certificate or would like those slides from today. We also put a direct link to our YouTube channel, which this presentation will be on there shortly. And if no one else has any questions for Mr. Roche, then we can, Wayne would also like to know, choker stone was limestone or channel run?
So we didn't use a choker stone in this test study, but I believe the choker stone used in that previous study in 2014 was just a number 4 coarse aggregate. But I'm not sure on the exact material. So all the stone that we used fit the Iowa DOT gradation and material, and I believe was a granite.
Okay. I'm not seeing any more questions out there. So, Brian, thank you again. This was a great presentation. Again, it'll be up on our website and our YouTube channel. If you guys have any questions for Brian, his information is on the screen. And feel free to reach out for anything else for me. I'm going to quit recording.